Starting here. Okay, this variation in charges is very helpful. That's called the oxidation state, or the oxidation state range, or we'll just say charge range here. Charge, in other words, oxidation state. There are different charges that we have. One of them is called the oxidation state. We'll talk about this in more detail later, but it's the range. And so it's helpful for helping us figure certain things out. So, like carbon has six electrons. You know, helium has 2 electrons. Neon has 10 electrons. And so it could go -4 gets us to 2, or +4 gets us to 10. And so the carbon's oxidation state ranges from -4 all the way up to +4. We don't expect it to go outside this range. Usually the 8s refer to the highest positive, like carbonate, it's going to be the highest positive. Nitrate, you know, nitrate is NO3 minus. And so if each oxygen is -2, we have 3 of them, that's -2 times 3 is -6. That means nitrogen must be +5. So 5 positive charges, 6 negative charges, adds up to -1 net charge. And so we add up or combine all these charges, we end up with a net charge of -1. And so nitrate's a -1 ion. Well, +5 it's max because, you know, nitrogen has 7 electrons. If it has 7 electrons, if it loses 5 of them, it's at 2. It could also gain 3. And so nitrogen's going to vary from excuse me, I should do it. -5 electrons would be +5, you know, and so to -3. So its charge varies from -3 to +5. You have 3 extra electrons to go to neon. Probably be easier to gain 3 extra electrons, and so we end up with N3 minus, which would be nitride. And so let's look at these now. N3 minus is a nitrogen with 10 electrons because it has 3 extra negative charges, which gives us the -3 charge. And then we have nitrate. Nitrate, we just analyzed. This is nitrogen in the +5. Now, this is, with a free ion, sometimes we write these in terms of Roman numerals. So this would be +5 Roman numeral, because it's not literally, I mean, because it's stabilized with these oxygens here. So that would be +5. However, nitrite is not there. Nitrite, what would the charge on nitrite be if oxygen's -2? So if I have oxygen at -2 plus the nitrogen at plus blank is equal to -1, the net charge. So what is the charge here? And so that's -4. This is going to be +3. So in other words, nitrogen's in the +3. Well, that's okay because it's inside the range. Inside the range is okay. Outside the range is not okay. So this is nitrate. However, would we expect per nitrate to exist? Now, per nitrate would be NO4 minus. So would you expect per nitrate to exist? And so in this case, well, oxygen's -2, so I have 4 of those. Nitrogen is plus something, and then this has got to add up to -1. So -2 times 4 is -8, -8 plus 7. So if I had per nitrate would have a nitrogen +7. Is nitrogen +7 in the range of -3 to +5? No, it's outside the range. So +7 is outside. That means it goes past in fact, it loses all of its electrons, and that's not feasible. So per nitrate does not exist. There's no such thing as per nitrate. However, for chlorate didn't correspond to the max. You know, chlorate was just ClO3. The max is ClO4. And so that's where they got it wrong. They didn't know about perchlorate. And they didn't know about perchlorate because it wasn't so stable. The 8s came historically. You know, these are the most common. We live in a very, what we call oxidative environment. So it's usually things are oxidized to its max. The same thing like this, like if you burn natural gas, you know, let's say we burn some methane, which is mostly natural gas, CH3. If we don't have enough oxygen, then we form other products like soot. Soot is just carbon particles, you know, that's soot. It's carbon. Or carbon monoxide. We don't want to form carbon monoxide. Soot is a solid. Carbon monoxide is a gas because this is poisonous. Carbon monoxide is poisonous. Carbon dioxide is poisonous too, but a lot less poisonous than carbon monoxide, you know, it's a lot less toxic, but we form carbon dioxide. And so what we want to do is we want to make sure we do complete, you know, we burn it completely to carbon dioxide, but why stop at carbon dioxide? Why can't we burn it to carbon trioxide? Why can't we burn it to carbon trioxide? Well, carbon trioxide doesn't exist. Why? Well, if oxygen's -2, what would that make carbon? Close, not 7. If oxygen's -2, because this is neutral, and so we have 3 oxygens at -2, plus 1 carbon at plus something is going to equal 0 because carbon trioxide is neutral like carbon dioxide. It's not an ion. It's 6, right? So that goes beyond the range. You know, carbon's going to lose 4 and stop at helium. And so it's outside the range here. And there's good reason. In other words, it would lose all 6 electrons, and that's not feasible. So carbon trioxide doesn't exist. But you might say, hey, didn't we see carbon trioxide before? Yeah, you might say, didn't we see carbon trioxide? I saw it here. Isn't this carbon trioxide? No, this is not carbon trioxide. This is called carbonate. And when we look at the charge on carbon and carbonate, it's +4. It's going to be +4 because +4 minus 6 gives us -2. And so +4 is okay because that's in the range of oxidation states or range in charges that we expect for carbon. And so having some knowledge of this range, you know, can help us. For example, the max positive charge on phosphorus is +5, but it could be -3. So the charge on phosphorus varies from -3 in phosphide, this is phosphide, to +5 in phosphate. Now the +5, you know, that's not the free atom. It's not the free atom. It has to be stabilized by having the oxygens there. But if we have 4 oxygens and -2 each, so -2 times 4 is -8, then phosphorus must be +5. So in this case, we don't expect perphosphate to exist. Perphosphate shouldn't exist, but phosphite could exist, of course. Phosphite. It's just for the halogens that we have the pers, okay? And like perbromate. Perbromate is BrO4 minus. If we have perbromate like this, then oxygen's -2, -2 times 4 is -8. That means bromine's got to be +7. Well, that's okay. +7's in the range because these guys range from -1 to +7. -1, like fluorine, goes from 9 electrons to 10 electrons. +7, well, it goes from 9 electrons to 2. You know, chlorine 17. So +1 electron gives us 18. Or -7 electrons gives us 10, you know, like that. Okay, so those types, little things can help us ease the burden of memorization, you know, if we see some patterns. And memorizing patterns is easier than memorizing individual, you know, species. Okay. All right, so let's get some practice with this. Now, naming ionic compounds, we just need the name of the cation, space, name of the anion. And so we could do that for ionic compounds. And let's take a look at some ionic compounds here. So come on. All right, I was hoping to get this one. That looks pretty decent. Let's take a look at this one. Hopefully they don't have to make. So here's the formation of the ion. So if we take atom of sodium and lose an electron, the proton to electron ratio is unbalanced. So we end up with a positive charge here. Like that. This is showing it diagrammatically or pictorially here. So this is the sodium cation with the chloride anion. So this is called sodium chloride. All right, let's get some practice here. The practice I want to do is, first off, let's do the practice from the supplement. Here. All right, these ones we get from the periodic table, you know. These are fixed charge guys over here. We talked about these. And so the name of these fixed charge, we can get the charge based on the column number, right? Zinc, cadmium, these are the little L. You know, this is the island of fixed charge species, but the rest are pretty easy from the periodic table. These are pretty easy too, because this is in group 2B. I mean 1B, and these two are in group 2B. Off the periodic table. This is what I'm talking about, 1B and 2B. It depends on what periodic table you have. And so let's take a look at the variations and how they do these periodic tables here. Let's see. Okay, that's one. Okay, 11 or 12. Let's see if I have an older style periodic table here. Okay. Here, do you see how they do this? These usually refer to the maximum positive charge that we see. The max positive charge, 1 plus 2 plus 3 plus 4 plus 5. And then it kind of tops out manganese plus 7, iron, cobalt, nickel at plus 8. And then we go to maximum positive charge at plus 1. However, this is a rule, not a law, because gold is plus 3. Copper is plus 1 and plus 2. Silver is only plus 1. And then 2B, zinc is always plus 2. Cadmium is always plus 2. Mercury's maxed out at plus 2, but it's also plus 1. Right? 3, 4, 5, 6, 7, 8. 8 we don't see, you know. These ones don't react. But this is kind of the max positive charge here that we see in this style of periodic table here. That's that one. All right, let's take a look at some practice for nomenclature. Oops, what did I do with that? Here. And here, you know, plus 2, plus 3. This is in the plus 2, plus 3 are very common in the left side of the transition elements. On the left side of the transition elements, plus 2, plus 3, plus 2, plus 3, plus 2, plus 3, 2, 3, 2, 3. Okay, this is on the left side. In the middle, plus 1, plus 2, plus 1, plus 2, plus 1, plus 2. Now this plus 1 is very funny. This is the diatomic. We have 2 atoms with a total charge of 2 plus, which means each atom's plus 1. So it's a mercury 1 or mercury positive 1 ion, mercurous ion. Okay, that's in the middle. So the middle, plus 1, plus 2. On the left end is plus 2, plus 3. On the right end, it's 2, 4. So tin and lead on the right end of the transition. Well, these are getting into the main group now. That's 2, 4. So the charges aren't difficult. You just got to look at the periodic table and see where the position is in the periodic table. You can figure it out. There are more charges than this. Here, mercury is a polyatomic cation. And so here are the 2, 4s, the 1, 2s, and the 2, 3s. Okay, then let's continue here. So these ones, these are easy because they're just off the periodic table, and you got to know if you're fixed charge, do not use Roman numeral. If you're in the variable charge region, use the Roman numeral. The silver And silver, zinc, and cadmium, or zinc, cadmium, silver, this is a little sea of fixed charged ions in the variable charge ocean. That's the way I picture those. So then we go to monatomics here. With the monatomics, you just change the ending to "ide" and then figure out how many electrons it wants to get to the nearest noble gas. Nitride. Nitride, we know the charge. It's got to be 3. Phosphide, 3. These are monatomic anions. Hydride, you know, hydrogen can gain 1 electron, so it would be like helium with 2 electrons. Fluoride, chloride, bromide, sulfide, oxide. Monatomics. Polyatomics, you know, some of these we just memorize outright. You know, so ides usually mean monatomic, but there are some ides that are polyatomic, like cyanide, hydroxide, peroxide, those. Which ones do I memorize? Which ones do you have to memorize outright? The ones that you got to memorize outright, acetate for sure. That's going to be a memorization. Ammonium, memorization. Chromate, dichromate, cyanide, hydroxide, peroxide, oxalate, permanganate. These ones you memorize. These guys I get off the pattern. So all these, I don't memorize any of these. Iodide, I don't memorize that. And so these are off the periodic table. And then we have little variations, you know, the hydrogen, you know, that's easy, just add a H+. And then is thiosulfate here? Let's see. No, thiosulfate's not here. But remember what we do with thio. Okay, so let's take a look at acid names. Acid names, remember we only have 3 variations for acids, you know. And so these are all ides. Fluoride, chloride, bromide, iodide. Those are all ides. So if there's an ide, then it's hydroic acid. Hydroic acid. And so whenever we have an ide, chloride, fluoride, hydrofluoric, chloride, hydrochloric, bromide, hydrobromic, iodide, hydroiodic. This is an 8. This is phosphate, so phosphoric acid. Sulfate-ic acid. Sulfite, ous acid. Carbonate-ic acid. Nitrate-ic acid. Nitrite, ous acid. Acetate-ic acid. Oxalate-ic acid. Perchlorate-ic acid. Chlorate-ic acid. Chlorite, ous acid. Hypochlorite, ous acid. And so just 3 variations of that we worry about there. Eventually we're gonna, when we get to acids in more general, there are strong acids and weak acids. So these ones with the asterisk are strong acids. The others are weak. 1, 2, 3, 4, 5, 6, 7. There are more than 7 strong acids. These are the 7 common strong acids. And eventually you'll have to memorize that. But for right now, you don't have to worry about the 7 common strong acids. Hydrofluoric, it turns out to be a weak acid, but these 3 are strong, plus the sulfuric, nitric, perchloric, and chloric acid are strong. What happened to nomenclature? Oh yeah, nomenclature is exercise A. So where is exercise A? It's probably way down here. Chemical reactions and equations, not that. Net ionic equations, no. What we were talking about earlier about the charge is something called oxidation state or oxidation numbers. We haven't gotten to this point yet. but we can look at the charge range of certain species, you know, and it's going to fall within that range. I'll talk about that later. Electrolytic voltaic cells, no, not that. I moved it. I didn't look at the latest edition of this. I should look at the table of contents. Better. So let's look at naming these anions here. Perchlorate, iodide, bromide, chloride, hydrogen sulfate, chlorate, nitrate, etc. This is just practice. Oh yeah, boric acid. Boric acid is important in eye drops and that kind of stuff. Borate. Common acids. Let's see. Is there a table of contents here? Table of contents. This is divided into two. And so this is the supplement first, and then there's the lab. So it's going to be in the lab section. Sorry, should have looked at this before. So the second part of this is lab manual, the second half. So you have to go into the middle of this thing to find it. And so these are the labs we're doing. Ah, shoot. All right. I guess I wasn't involved in the revision of this, but it looks like they got rid of it. Yeah, they got rid of it. All right. Let me do something really quick here. Actually, that's not one, but actually that'll probably do. That one didn't have enough examples. This one's better, probably. This is something I did for Chem 1A. I'll put this on. I'll post this on Piazza, probably. Acids, this is too many variations. I just like ate, and I'd. So I'm going to rotate. Okay, we're going to go through these rapidly and then we'll take a look at the homework, but we just want to practice here. And so this one, AG is called what? What's the name of AG? Silver, yeah. Is it fixed charged or variable charged? It's fixed, good. It's fixed charge, so we don't need a Roman numeral. In fact, it's only +1, and the Br is a -1. So this is called silver bromide. And so we'll do a bunch of examples here, and then maybe I'll let you add it. Okay, Pb is called what? Lead. Is it fixed charge or variable charge? not fixed, it's variable charge. So we have to figure out what the charge is. So we look at CO3. What's CO3 called? CO3. And what's the charge on CO3? It's carbonate, and carbonate is 2 minus. So this has got to be Pb2 plus. Plus 2 minus 2 gives us 0. There's no charge. This is called an ionic compound or a salt. And so when we're putting together ions like this, it's either a salt or an acid. And so this would be a salt. Or, you know, it could be a ceramic also. But we'll just call it an ionic compound. And so we're looking at ionic compounds here. This is going to be lead. And since it's variable charge, we have to do it like this. Lead, Roman numeral 2. There's no space here, carbonate. So this is lead 2 carbonate. Zinc, variable charge or fixed charge? Zinc. Look at it on the periodic table. And when you look at it on the periodic table, it's fixed. It's in the little island of fixed charges. Zinc is always 2 plus. Oxygen likes to be 2 minus, you know, to be happiest. And so we don't need a Roman numeral for this. Zinc is spelled with a C. Zinc oxide. Oxygen with a -2. Copper, fixed charge or variable charge? Copper is variable. +2 + 3, +1 + 2, or +2 + 4. Look at it in the periodic table and tell me what region it is. Is it in the +2 + 3? That's the most common charge. +1 + 2 or +2 + 4? It's actually in the +1 + 2. So is this copper 1 or copper 2? Well, it depends on SO4. SO4 is sulfate and SO4 is 2 minus. So this must mean copper is a 2 plus. 2 plus -2 gives us 0. We only have 1 copper. And so this is, we need the Roman numeral here. And so this is copper 2 sulfate. Copper is the higher charge. This is 1, 2. So this is also called cupric sulfate. This is also called plumbus. +2 is the lower charge, +4 is the higher charge here. And so lead is 2, 4. And so this would be plumbus, carbonate. This would be cupric. Now both of these have 2. It's relative. It's not having a +2 charge tells you if it's ic or aus. These are the old names. Plumbus, it's the lower of the charges because the higher one's +4. This one's the higher one because the lower one's +1. Okay, aluminum, fixed charged or variable charged? Aluminum's fixed and it's always +3 based on its position in the periodic table. You know, and then OH is a minus, and so we have 3 of those. These are called hydroxides. And so we got 3 of those. Should we call aluminum trihydroxide? Now that's a common mistake. We don't call this aluminum trihydroxide. The reason we don't call it trihydroxide is we know we already have to have 3. We have to have 3 hydroxides in order to balance out this 3 positive charge. And so this is fixed charge, so we don't need the Roman numeral. So it's just called aluminum hydroxide. Aluminum hydroxide. Now, we don't need a tri here because the only way you can make aluminum hydroxide neutral is by having 3 hydroxides. So it's redundant information that we don't need. And so just aluminum hydroxide. Is cadmium a fixed charge or variable charged? So look at it on the periodic table, fixed. And what is its charge? It's fixed at +2, good. And so cadmium's always +2. Sulfur, what's its charge? Well, sulfur's charge varies, but its most common charge would be -2. It's just 2 electrons short of being the nearest Nobel gas. And so this is the cadmium ion and sulfide. It's called cadmium sulfide. Okay, let's take a look at this. We saw silver before. Silver is always +1, right? Ag is always +1. What is NO3? Charge. The charge on NO3 is, look at it on the periodic table. Remember, we start out borate. Borate's -3. Then we go from boron to nitrogen. Actually, what do we do? We'd go boron to, no, I think I got that wrong here. Let me look. So borate is BO3, 3-. Boron, then carbonate is CO3, 2-. And the nitrate is NO3-. So NO3's got to be minus. And this would be nitrate, right? And so this is silver nitrate. No Roman numeral necessary here because silver is fixed charged. Now here, this is an acid. We recognize this as an acid because of the H here. And so we need to know what the anion is. The anion in this case is ClO3-. So is chlorine 3 oxygen or 4 oxygen species? So we go FO3- ClO3-. So it's a 3 oxygen 8. And so this is chlorate. If this is chlorate, then what is the name of the acid? What would the name of the acid be? If this is chlorate, what is the name of the acid? Yeah, chloric acid. That's correct. And so this is chloric acid. Now, there's going to be a distinction here. Now, let me tell you about the convention here. We have 2 names for HCl. Depending on pure HCl. Pure HCl is a gas. And then we have a common mixture when you take HCl and dissolve it in water. And this is AQ. AQ means aqueous, which means dissolved in water. Dissolved in water. So if we take pure HCl gas and dissolve it in water, we form HCl aqueous. This is what we call the acid here. Acid. And so the acid is, we name it with the acid name. And so this is chloride. Cl- is chloride. Chloride. And so it's a D. So what do we do when we have an ide? What do we call this acid? This is chloric acid, and so we can't call this chloric acid. This is chloric acid. What is HCl, aqueous? Hydrochloric acid, and so that's correct. This is hydrochloric acid, hydrochloric acid. Okay. With hydrochloric acid, the other name for this is we name it as an ionic compound. And so when it's in the gaseous phase, name as ionic compound rather than an acid. And so we have the hydrogen ion, which is fixed charge. We don't need a Roman numeral for that. It's always +1. So we have hydrogen. And the anion is chloride. So this is called hydrogen chloride gas. Hydrogen chloride gas is pure. And so this is just a rule, rule of convention. Convention is you name HCl gas hydrogen chloride gas, and HCl aqueous would be hydrochloric acid. The same thing with HF. HF gas, this is called hydrogen fluoride gas. Fluoride is FLU, not FLO. That's a common misspelling, is people write it like flour, but it's not flour, it's fluor. Hydrogen fluoride gas. And then if I have HF and take that and dissolve it in water to make the mixture, the acid mixture, this is called hydrofluoric acid. Hydrofluoric acid. It's an example of that. All right, we saw lead is a variable charge. And so is this the +2 or +4? Well, what is CrO4 called? CrO4, and what is its charge? CrO4 is called chromate. Chromate is, the spelling on chromate is, yeah, 2 minus is the charge, good. The spelling, there's an H in there, ChROMATE, that's chromate. And so that means the lead has to be 2+. Lead is in the 2,4 region on the right side. Right side's 2,4. And so this is the lower charge. And so this would be called lead, Roman numeral 2, chromate. Now the lower charge gets the Aus. So this is called plumbous ion, plumbous versus plumbic. Plumbic would be lead 4. And so you could call this plumbous chromate or lead 2 chromate. All right, we know chloride. Chloride is -1, and we have 2 of them. And therefore, mercury must be, well, mercury is what we call a diatomic ion here. And so it's 2+, it's an Hg2, 2+. And each mercury is 1 + 1. But we have 2 of them and they're linked together. This is why we can't separate it. You know, it's linked together. And so this is actually called mercury, Roman numeral 1, because each mercury is a +1, not the total charge, which is +2. So it's not Roman numeral 2, it's Roman numeral 1. Mercury 1 chloride is the name of this stuff here. Now, mercury is a +1 + 2. So +1's lower, so that gets the Aus. So this is also called mercurous. Mercurous chloride. There. Let's go on to this one, CaCO3. Well, Ca is fixed charge. That's 2+. Based on the periodic table. And then we know carbonate, we saw that before, CO3 2-. And so this one is called calcium, no Roman numeral needed there, carbonate, calcium carbonate, also known as calcite in the mineral form or calcium carbonate in the rock form. Okay, copper is variable charge. What are the charges, the common charges on copper? Is it +2 + 3, +1 + 2, or +2 + 4? 2, 4? So 2, 4 is on the right side of the periodic table. And take a look at the periodic table. Is copper on the right side or kind of in the middle? On the right side being close to tin lead. Yeah, it's a +1 + 2 actually. And so is this copper 1 or copper 2? We don't, well, nitrate we know. This is NO3. NO3 we know is -1. If we have 2 -1s, that means this has got to be a copper 2+. As I got 2 plus -1 -1 gives us 0. And so I need 2 nitrates to balance out the +2. So this has got to be copper, Roman numeral 2, nitrate. Copper, Roman numeral 2, nitrate. Or copper 2 nitrate. So you can write that out there. Magnesium's fixed charged. So, oh, is 2 the higher or the lower charge? Higher. So this is also named as cupric nitrate. It's higher charge. Magnesium's fixed charge, that's +2. Sulfate is -2. So this is just magnesium sulfate. Number 15, magnesium sulfate. MgSO4, magnesium sulfate. Let's continue on here. Clear the drawings. Go on to number 16. Barium's in the same family as magnesium. It's fixed charged, +2. So this is Ba2 plus. C2O4, what, this has got to be 2 minus. And what's this called? C2O4 2 minus called? Oxalate. And so this is barium oxalate. Oxalate. Okay. Okay, this one, usually phosphorus is a non-metal. Phosphorus could be +3. It'd be variable charge, you know, that's one. And so if you were to name this as an ionic compound, its name would be like this. If we name this as an ionic, phosphorus would be variable charge because phosphorus, remember, in phosphorus, it would vary from -3, if it gained 3, to +5. +5 here. And so in this case, we have 3 chlorides. Each chloride is -1, and that means phosphorus must be plus what? To balance out the charge. If I have 3 negative charges, then phosphorus must be 3 positive. And so one way of naming this is phosphorus, Roman numeral 3, chloride. If we named it as an ionic. But one thing about ionic compounds are typically metals plus a non-metal. Well, phosphorus is non-metal. And so what we really should do is we should name this as a molecular compound. And in fact, this is a binary molecular compound. Molecular compounds are typically made up of non-metals only. Binary molecular compounds, we name it like this. It's named phosphorus trichloride. Now, these are rules of nomenclature. So what do you call it? Are you going to call it phosphorus 3 chloride or should you call it phosphorus trichloride? Which one do you call it? And so let's take a look here. Well, if I type in phosphorus 3 chloride, I get phosphorus trichloride and I got phosphorus 3 chloride. Let's see if we order this. If we order this chemical, what do they call it? So I go to Fisher Scientific and let's order a bottle of this. It's $25.80 for how many grams? 50 grams. 50 grams, $25.80. So this is phosphorus 3 chloride. They're naming it as an ionic compound. Do you see that? But they also show like synonyms. Synonyms would be phosphorus trichloride. Let's see all the synonyms here. Phosphorus trichloride, trichlorophosphine, phosphorus chloride. They try to come up with all these variations of the names, you know. There's IUPAC, is an international union of pure and applied chemistry. IUPAC stands for International Union of Pure and Applied Chemistry. They call it trichlorophosphane. Okay, we don't want to have to deal with too many names. But for binary, for our book, phosphorus trichloride is the preferred name for this stuff. But you have to be aware of other ways of naming it because, you know, if I went to the catalog doesn't call it phosphorus trichloride. The catalog in this catalog, the Fisher Scientific catalog, they call it phosphorus 3 chloride, like the ionic compound. So should you call it? You should call it phosphorus trichloride. We're going to name it as a binary molecular compound. It's like water, you know, try to come up with all the names that you can for water, using all the different rules. And so phosphorus trichloride is what we're going to call it, AKA phosphorus 3 chloride. ALP. Now, names like this, you know, here phosphorus is the cation. You can see kind of in this phosphorus 3, it's +3. In this case, phosphorus is the anion, because remember, phosphorus charges vary from negative to positive here. In this case, aluminum's fixed charge. So aluminum is always +3. And that means the phosphorus, we can figure out the charge here. If aluminum's +3, then phosphorus must be 3-. And so ALP is called aluminum, no Roman numeral necessary here, phosphide. So we just changed the ending. It's monatomic anion, and the charge is off the periodic table. So aluminum phosphide. That's it. Sodium's fixed charge at +1. What is ClO minus? Well, ClO minus, it's got to be a negative charge to balance out that. Now this is not this is not chloride and oxide. It's not what we call a mixed anion. Sometimes we do have mixed anion species and mixed cation. You have to recognize a ClO coming together as a package, you know? And so we don't split it up. We don't say, okay, we have a sodium here, a chloride, and an oxide. It doesn't work. The charges don't work either, because sodium is plus, and this whole thing is -3. And so what happens is, who gets the charge? Well, oxygen gets the charge. That leaves chlorine out. Chlorine has to suffer because oxygen turns out to be stronger. So oxygen gets its charge of -2. That means chlorine has to be +1 in order to give a ClO with a minus charge. And so chlorine's a loser. Yeah. We'll look at that chemically later on when we look more at chemical properties and that kind of stuff. And so it's not fixed, it's not separate, two separate ions. It's one combined ion, ClO minus. It's all combined, not two separate ions here. Not a separate chloride and a separate oxide. But as I said before, sometimes we do have separate, you know, what we call mixed anion or mixed cation species. Let me go through something really quick because it's like not the AC. Back. Some people like the AC super cold when it's hot outside. It's too much of a thermal shock for me. But anyway, here, sodium, what's this anion called? And so when we look at chlorine, chlorine's in the 3 oxygen block. And it's charged -1, so that's chlorate. So this would be chlorite, ClO2 minus. This must be hypochlorite, ClO minus. And so this is bleach, AKA bleach. Sodium, bleach is a mixture of water with this. This is actually a solid salt. So if you take sodium hypochlorite and dissolve it in water, we get bleach. Bleach is, depends on how strong the bleach you get. Bleach is pretty dilute solution. Dilute meaning there's not much sodium hypochlorite, lots of water. So sodium hypochlorite. Potassium's fixed charge, you know, +1. What's CN? CN's taken together, it's a package. It's what we call a polyatomic anion, just like ClO, we don't separate it. Cyanide, good. Cyanide's -1, and so this would be potassium. How many S's in potassium? 1 S or 2 S? 2 S's, yeah, there are 2 S's. So potassium cyanide, cyanide. Potassium cyanide is pretty toxic stuff, so you got to watch out for cyanide. Cyanide loves hemoglobin. in your blood and prevents oxygen from attaching. This is one of the most common chemicals in lab. Fortunately, potassium cyanide is not that common, but this is very common. One of the most common, like hydrochloric acid, this and a few others are very common. This one, sodium is a fixed charge at +1. What is OH? It's not two separate ions, it's one packaged polyatomic ion called hydroxide, and it's got a negative charge to balance out the charge. Sodium hydroxide. Sodium hydroxide is what we call a base. Bases have kind of the opposite chemical behavior than acids. You know, the opposites of the acids. Now this one is tricky. When we look at this one, okay, hydrogen. Well, hydrogen is variable charge. Hydrogen can be plus or it could be minus. If hydrogen's plus, we call it hydrogen ion. If it's minus, we call it hydride. Now oxygen's tricky. Oxygen's preferred charge is -2. And so anions aren't written first. We know it's not hydride because if it's hydride, it would be written second, not first. Cations are written first. So this has got to be H+. And so what we have is we have two H pluses. Now if oxygen gets its preferred charge, that would be two oxygens at -2. So that's -2, -2 is -4. -4 plus 2 doesn't add up. This has got to be 0. So oxygen suffers in this case, but hydrogen can't lose any more electrons. If it could lose more electrons, then it might go to +2, but hydrogen only has 1 electron to begin with. So you'll never see hydrogen +2. It just can't exist as it's element number 1. And so what this means is the oxygen has to be -1 and -1. Well, oxygen at -1, we call O2 2-. It's a polyatomic. These oxygens have to be paired up. And O2 2- is called peroxide. And so this is hydrogen peroxide. Now, when the oxygens link up, it's not so happy. And so what we end up is with a negative charge on this oxygen and the negative charge, I circled the negative just to emphasize the charge. And this is called a peroxide bond. This oxygen-oxygen single bond is not happy. It's an unhappy bond because there's reasons for it. Maybe we'll talk about that later, but it has to do with the distance between the nuclei here and destabilizes that. So this is why, like in dichromate, we try to avoid these oxygen-oxygen single bonded links like this. You know, ATP, ADP, same thing. Try to avoid those. Hydrogen peroxide itself is unstable. Yeah, so decompose. Now look at this hydrogen. This hydrogen is not written at the front. If the hydrogen is written at the front, I'd call it positive. This hydrogen is written at the end. So this hydrogen is written at the end. It's got to be an anion. And so this hydrogen must be a negatively charged. Well, the only negative charge on hydrogen is -1. Then it's like helium. And so this is hydride here. Sodium, this is going to be positive charge here. And so this one is called sodium hydride. Sodium hydride. Now this is tricky here, the next one, because how do we separate these things? Well, the first one is potassium. However, we aren't going to separate these. These are not two hydrogen ions, and these are not two hydride ions. This is an H2PO4. Now, PO4 is normally 3-, but if I have two H's stuck on there, then the charge changes to minus. And so this is H2PO4-. Do you recognize that? Well, I recognize phosphate, and if I have a hydrogen on there, I call it, So this is called potassium dihydrogen phosphate. Potassium dihydrogen phosphate. Okay, the same thing here. We have to recognize how to split things apart. This is going to be a potassium, but this whole thing stays together as an MnO4-. And so the charge has got to be -1 because they have to neutralize each other, at least in an ionic compound. So this is potassium, and what's MnO4 minus called? Permanganate. That's good. Potassium permanganate is correct. Potassium permanganate. Okay, let's look at some more examples here. Potassium permanganate to this one. Okay, now this begins with an H, so there are two ways of naming this. One, we could name this as an ionic compound, or we could name this as an acid. If it's not specified here, like, you know, in the previous example, it was specified gas, AQ. If it's not specified, we name it as the acid. And so we're going to name this as an acid. So what is the anion name for that? You have to look, okay, start at boron and start at silicon and then work across. This is what I do. First I look, is it a 3 oxygen or a 4 oxygen species? So I look at the periodic table. And so looking at the periodic table, I first figure out 3 oxygen or 4 oxygen. 3 oxygens are this elbow here. These all have 3 oxygens. 4 oxygens are the inner block here. These are all 4 oxygens. So 3 oxygens, 4 oxygens. So chlorine is 3 oxygen. So ClO3, that's chlorate. Chlorate. And then the charge, so it goes -3, -2, minus. This is minus. ClO3 minus is chlorate. That's how I do it. So let's take a look back here. So if it's chlorate, then it's chloric acid. Exactly, correct. Adriana, good. Chloric acid is the name of that. Chloric acid. Okay, this one, how do we split it up? Well, the way we're going to split it up is we're going to sodium and then the HCO3. Well, that's got to be an acid anion, HCO3, and the charge on that is carbonate is usually a 2 minus. Yes. Goes boron, which is 3 minus, borate to carbonate, which is 2 minus, 3 minus, 2 minus. And then we have a hydrogen on there. If we have a hydrogen, that changes its charge to minus. Is this chart on Piazza? This chart here? No, it's not. I'll put it on Piazza right now. I didn't put it on Piazza. It's time for our break anyway. So let me put this, I forgot, I thought we had the nomenclature lab. I didn't put this one on Piazza because we used to have exercise A in our Chem 4 supplement, which has disappeared on this version of the supplement. Maybe it's still there. Maybe it just didn't make the table of contents, but let me take a quick look and see if exercise A is there, but just not listed. Here. So I'm going to look for nomenclature problems. I'd like to pass this out, but unfortunately I can't email this to you. You're supposed to purchase this because of copyright. So it's gone. Nomenclature's gone. So we're going to do that instead of this. This handout which I have here is the Chem 1A, what I use for Chem 1A. Well, Chem 1A and Chem 4 are similar. I just have the students memorize more, like cyanate and a few more, but otherwise it's the same thing. And so I'll post this on Piazza now. Okay, let's take a break, and then I'll post this right now, and then you can grab it off Piazza. So I'm going to pause the recording.